So in this video by proof by induction, I'll be proving that for an integer n greater than or equal to 1, so n belongs to the integers, the sum from k equals 1 to n of k times 2 to the k is equal to n minus 1 times 2 to the n plus 1 plus 2. So this is basically my statement Pn. Okay, and if you want to see this more clearly, my statement Pn is just saying 1 times 2 to the 1 plus 2 times 2 to the 2 plus 3 times 3 to the 3 and so on, plus n times 2 to the n. That all of this left hand side is equal to n minus 1 times 2 to the n plus 1 plus 2 plus 2. So that's my statement Pn. Okay, so remember, a proof by induction takes two parts. The first part, which is relatively simple, is the basis step. Okay, so the first part is the basis step. Okay, so in this case, it's given in the question that n is greater than or equal to 1. So the smallest value of n at which Pn is valid is n equals to 1. So that's my smallest value of n equal 1. Okay, so basically what I need to check now is I need to check if P1, the statement P1, is true. So in other words, if I plug in one in this sum over here, right? If I plug in n equals 1 in this sum, then I want to see if both sides give me the same thing. Okay, so let's start from here. So my sum is going to be from k equals 1 to n. So in this case, it's going to be sigma k equal 1 to 1, since n is 1, of k times 2k, and I want to see, so I have my question mark over here, I want to see if that's equal to n minus 1 times 2n plus 1 plus 2. Okay, so I'll do my left hand side and my right hand side and see if they're the same. So LHS is equal to sigma k equals 1 to 1 k times 2k, 2 to the k, and that's just 1 times 2 to 1, because that's my only element of the sum, so I don't need to write anything else. So in other words, this is just, so my LHS is just 2. Okay, and then my RHS, my right hand side, I just plug in 1 wherever I see an n, so it will be 1 minus 1 times 2 to 2 plus 2. So this is 0. This is 0. And so I'm left with 0 plus 2, which is 2. So I can see that my LHS is equal to my RHS. So LHS, right, left hand side is equal to right hand side. So that means that, so P1 is true. And so I've proven base case. Okay, and I'll put a little check mark. Okay, so that was my basis step. Now my inductive step. Okay, so inductive step. So remember, what you do in an inductive step, you assume that Pn is true and you try to prove for Pn plus 1. So assume that Pn is true. In this case, Pn was that sigma k times 2 to the k is equal to n minus 1, 2 to n plus 1 plus 2. So sigma k equals 1 to n, k times 2 to k is equal to n minus 1 times 2 to the n plus 1 plus 2. Let's see, did I get this right? Plus n minus 1. Yeah, okay. So this is what I'm assuming. I'm assuming this is true. So assume is true. So I'm assuming this is true. Okay. So in other words, I'm saying that I know. Well, not that I know, but I'm saying that I'm assuming that 1 times 2 to the 1 plus 2 times 2 to the 2 plus and so on plus n times 2 to the n is equal to n minus 1 times 2n plus 1 plus 2. Right? So this is also, all of this is also Pn. Okay, so I'm assuming Pn is true. Okay, so now what I need to do, so that's my assumption. Now what I need to do, I need to prove, so my goal is to prove that Pn plus 1 is true. Pn plus 1 is true. So in this case, Pn plus 1 is the statement that, in this case, Pn plus 1 is the statement that k equals 1 to the n plus 1 times 2 to the k is equal to, and I'll just do it implicitly, so n minus 1 plus 1 is just n times 2 to the n plus 2, because I'm just adding 1 plus 2. Okay, so this is my statement Pn plus 1. So this is to prove. I need to prove this. Okay. Okay. So what I can do is I can start with my left-hand side. Usually when you see a summation in a proof by induction, it's always best to start with that, because you can sort of get something out of that sum. Okay, so let me write out Pn plus 1. So the LHS, the left-hand side of Pn plus 1, of the statement Pn plus 1, is sigma k equals 1 to n plus 1 of k times 2 to the k, which is just writing 1 times 2 to the 1 plus 2 times 2 to the 1 plus 3 times 2 to the 1. Oh no, whoops, sorry, I confused that. This should be 2 to the 2, and this should be, 2 to the 3, right? Because my k is here and here. So 1 times 2 to the 1 plus 2 times 2 to the 2 plus 3 times 2 to the 3, and so on, plus n times 2 to the n. Okay, let me just make this a bit smaller, plus n plus 1 times 2 to the n plus 1. Okay, so this is what I have. This is my LHS. So now what I'm going to do, I'm going to observe that all of this thing over here, this is the statement. This is the statement. Well, this is actually the left-hand side of the statement Pn, right? Remember, my statement Pn is this. So this is what I assume to be true, okay? But I have that here. So what I can do, I can use my inductive hypothesis. So this is the inductive hypothesis step, where I just replace this thing. I replace this thing by the right-hand side here. Okay, so this is what it's called. This is the inductive step. Okay, so this is equal to n minus 1 times 2 to the n plus 1 plus 2 plus n plus 1 times 2 to the n plus 1. Okay, so this was what I had before, and this is what I'm left with, right? So this was actually part of Pn. Okay, and this, by the way, I just said it. This is my inductive step. Okay. Okay, so now let's do a bit of rearranging, because remember what my goal is. My goal is for it to look something like this. Okay, so already I can just take my 2 out. I can put it aside because I don't really need it. So I'll put it on the left. So I'll put my plus 2 here, and then I'll write n minus 1 times 2 to the n plus 1, and then plus n plus 1 times 2 to the n plus 1. Okay, and now what I'm going to do is I'm going to factor my 2n plus 1. So factor 2n plus 1, and what I get is I get n minus 1 plus n plus 1, okay, plus 2. And I observe that my minus 1 and my 1 cancel, right? And what I'm left with n plus n. Okay, so that's actually 2 to the n plus 1 times 2n, right? Because n plus n is just 2n plus 2. Okay, so this is a part where you sort of need to think back to exponential and sort of power properties. Remember that if I have, let's say, if I have a to the let's say a to the m times a to the m, that's equal to a to the m plus m, right? Well, that's sort of what I have here. I have the same base here, so I have a 2 here, and I have this is like my n, and then I have the base 2 here, and then my exponent here is actually just 1. Okay, so what I can do, I can add n plus 1 to 1. And what is that really? That's n plus 1 plus 1. So I'll write that out. I'll write n plus 1 plus 1. And then you'll ask, okay, what happens with the n? Well, the n, we can just write it over here. N plus 2. Right? Because the n doesn't affect anything. It's like sort of a constant. It doesn't affect the power property in this case. Okay, well, what's n plus 1 plus 1? Well, it's n plus 2. And so I have, if I rearrange this, I have 2 times n plus 2 plus 2. Okay, and that really does look like what I wanted. That is, what I wanted to get at was, I wanted to get at that the sigma of k to the 1 to n plus 1 of whatever is equal to n times 2n plus 1 plus 2. And that's what I have. I have n times 2n plus 1 plus 2. 2 to the n plus 2 plus 2. Okay? And so my LHS is equal to my RHS. Okay? So P n plus 1 is true. Okay? And so therefore I can conclude that the statement Pn, which was, remember, that sigma k equals 1 to n of k times 2 to k, which is equal to n minus 1 times 2 to n plus 1 plus 2. So this statement, the statement Pn is true. And so my proof is done, and I've shown by induction that this sort of complicated thing with a bunch of sigmas and everything, and powers, is true.